It's my pleasure to introduce Davide Scaramuzza to all of you. He's an accomplished professor at the University of Zurich. I was told he's actually the most successful computing science professor at the University of Zurich, so we have the very best of the best here with us today. He works at the intersection of robotics and perception. He has actually many accolades in industry as well. So he was a co-founder of Zurich Eye, which actually got sold to Meta a few years ago and actually then became Meta Zurich. Recently, he's actually been working in agricultural drones, so it seems that his industrial career is far from over. And in terms of accolades, it's really hard because there is just too many. Like some that are very interesting, it will be just like you have a system from OpenAI that beat humans at chess. He has actually beat humans at drone racing. So he developed the first AI drone that was actually to be able to be world champion of drone racing at his own task. He also pioneered event camera systems from mobile robotics, and there is just too many awards to list on his pages. I had a challenge building this slide because there was just too much stuff and I had to pick. I picked three. As the previous speaker, he's also a recipient of an ERC Consolidator grant. He also has a stint in Vision, just to connect to 3DV, and was one of the best paper finalists for last year. And most importantly, actually, which is, I guess is still somewhat unannounced, but he's a recipient of what is the IEEE equivalent of a career award for 2024. So let me, give a loud applause to Professor Scaramuzza.
Thanks a lot for the nice introduction, and thanks a lot for inviting me here. It's really a pleasure and an honor to be speaking to the experts of 3D vision. In fact, I'm a 3D vision, okay, by training. I did a PhD in SLAM for self-driving cars, and then in 2009, I turned into flying robots in order to explore other challenges. And today, I want to tell you actually the journey that took me there, but I want to tell you this story from the perception perspective. And especially as Andrea mentioned, we recently announced in a paper that we defeated the world champion of drone racing with an AI-powered drone, and so I want to also talk a little bit about that. Maybe I can use that as a motivation for the talk, because there is a lot of 3D vision involved.
That is beautiful. One day, I dream I can achieve that. Damn!
That's not human.
Insanity.
I don't even know what I just
so
watched.
happy to see that in person. One day, I dream I can achieve that. Damn!
When I watch this video, I always get shivers, because it was 7 years of work and a lot of people involved. Also, just organizing this event was a big effort, and I'm really thankful to my amazing team and many students who collaborated. But so to get there, this is a story of perception. So let me rewind a little bit to a few years ago. Why did we start working even on drone racing? Why do we need agile robotics? Because that's actually the title of this talk, Towards Agile Robotics. It's a story of perception. You are all very familiar with the famous Roomba vacuum cleaning robots. They sold more than 40 million of these robots over the past 15 years. Until 2017, the robots were quite naive. They would bounce on the walls, and the average cleaning time of a 20 square meter bedroom was 20 minutes. In 2018, they mounted a camera and a small computer. They started doing SLAM, and the cleaning time went down from 20 to 5 minutes. So thanks to perception, the robot became more productive. Is it more productive than us humans? No. It takes me to clean such a bedroom around 1 minute. You may argue whether it's a good cleaning or not, but it still shows that we humans are much more competitive to machines. Where else has perception made a change in terms of productivity and agility? Well, you are all very familiar with the Boston Dynamics Atlas robots doing parkour. This scenario shows that thanks to perception, coupled with the model predictive control, you can actually do amazing things. Where else has perception made a change? For example, for space exploration. Actually, this is the first fully autonomous space robot on Mars. What about then the previous Mars rovers? Were they not autonomous? Partly. They were still controlled from the Earth. In fact, there was a 20-minute delay that was actually used to send waypoints to Mars, and then the robot would then autonomously reach the waypoint. But now you cannot control a helicopter from Earth because you need a continuous, real-time control. Perception is changing our field today. Thanks to perception, robots are becoming more autonomous. This is actually footage from a startup that we've co-founded, co-founded 3 years ago, which is doing crop spraying in the south of India using vision-based autonomous drones. So what we observe from these videos is that computer vision is making a difference. It's making mobile robots more autonomous than they were before. But interestingly, when you look around, you don't see autonomous robots. Why is that? Because humans are still the preferred solution in most of applications. Why is it the case that humans are still preferred? Because current robots are still far from human performance in agility, versatility, and robustness. And so I want to talk about two of these aspects today, agility and robustness. Now, robotics is a very large field. What is robotics is still really being debated. The robotics is platforms, is mechatronics, is mechanics, electrical engineering, computer science, is materials, it's sensors, it's many things. So it's difficult to talk about robotics in general without taking one specific platform into account. I started my research working on self-driving cars, and then in 2009, I turned into flying robotics. Why? Not because they fly, but because of the research challenges that they actually raise. And I will talk about that. So our dream in my lab is to make flying robots fly autonomously better than human pilots. You can say this is the motto or the vision of our lab, making robots fly better than human pilots. How do human pilots navigate drones? Vision-based. They put a camera on board the drone that transmits the images to goggles, and then the brain analyzes these images in real time and sends the control commands to your fingers. Initially, we thought that to be better than human pilots, we had to actually react faster than human pilots. And we were wrong, significantly wrong, to a point that actually this motivated a paper to indeed show our findings. What we found is actually that the reaction time of expert human pilots is 1/4 of a second. So it takes 1/4 of a second, so 250 milliseconds, to go from an image displayed on the screen of the human pilot to control commands. So it takes into account the time to process the image by the brain, plus the behavioral response through the nervous system to go until the fingers. So the reason why human pilots are actually better than machines is not because they are actually faster. In fact, they are slower. Our navigation algorithms take 10 times less time to send control commands to the drone than a human does. The reason why humans are better than machines is because they make better decisions in complex situations. And that's the reason why we don't have autonomous cars today. In case you didn't know, we humans are very good at driving. We make an accident every 10 to 100 million kilometers, depending on the country. So it's very, very difficult to build an autopilot in general. But why are we interested in making drones more agile? Well, to increase the robot productivity. This is actually a conclusion that can be extended to other robots as well. If we want robots to help us, or potentially replace us, they have to do tasks faster, more productively than humans. So we have to consider two things. First of all, drones, like quadcopters, multicopters, they can only fly for 20, 30 minutes. It's not much time, so you need to be very, very smart at making decisions. However, if you can fly faster, you can fly longer distances. So the drone becomes much more productive by flying faster. So does it mean that the faster you fly, the more productive you will be? No. In fact, as you can see in this plot, where we plot the distance in kilometers flown by a drone as a function of the flight speed in meters per second, you can see that for every drone there exists an optimal speed. That means if you fly at that speed, you are maximizing the range that the drone will achieve. So this one is a plot for a DJI Mavic drone, the most sold drone in the market. If you fly it at the optimal speed of 6 meters per second, you will reach the maximum range of 3.5 kilometers. But if you fly any faster, it will be no longer convenient to actually fly fast, because you will start drawing more energy from the battery because you encounter more air drag, and therefore, then actually you're flying less distances. Where are current commercial drone companies on this plot? Well, you will be surprised. These are the 3 world-leading drone commercial companies: DJI, Flyability, Skydio. And they are not taking full advantage of the optimal flight speed. Why? Because to fly fast, there are many challenges that we still have to address, even from a research point of view. But we know that one day we will reach this gap, but we don't know how long it will take. It can be 5, 10, 20 years, we don't know. But we will know one day we will always be flying at the optimal speed, because they are machines, so they can benefit from that. Where are drone racing pilots on this plot? Well, they are certainly not trying to maximize productivity. They are actually trying to maximize their chances to win the big pot of money by winning a race. But I believe that if we can gamify research, sometimes we can push the boundaries of research, because we hope that by solving difficult problems, those problems will actually help many other sub-problems. And this is actually something, so agility is something that, for example, for drones, will benefit a lot of sectors, search and rescue. Let me give you the example of Zipline. Zipline is a company based in California that has been delivering blood samples in Rwanda, Africa, for the past 7 years. They saved tens of thousands of people who were too far from the main hospital to be reached by an ambulance. By flying fast drones, they were able to save all those people. Exploration and inspection, forest monitoring. At the moment, the new X-Prize challenge is for fire extinguishment with drones. They want to fly swarms of drones to extinguish fires before they become big. And they need to be fast. Personal air vehicles, companies like Volocopter, they're already starting now, for example, to transport passengers, but they need to fly faster in order to be productive. What about space? We have all seen and witnessed the success of Ingenuity, the Mars helicopter sent by NASA. After 70 flights, now it was retired, but it was so successful that NASA decided to extend the mission, and they will launch 1 or more helicopters in 2030 that will actually fly more than 10 kilometers. In order to fly 10 kilometers, instead of the 300 meters of Ingenuity, they will need to fly the drone much faster than Ingenuity. So I hope with this I convince you why we need agile robotics. Now, we are not the first to address agile robotics. There has been plenty of works that have been done from 2006 until today for drones. So I decided to put most of these works on 2 axes. One that shows agility, and one that shows works that relied on external sensors, like GPS or motion capture systems. Actually, pioneering work was done by Andrew Ng and Peter Abil at Stanford in 2006, where they actually showed that they could stabilize a helicopter with the help of GPS and ground-based cameras. Following that work, Raffaello D'Andrea at ETH Zurich and Vijay Kumar at the University of Pennsylvania, where I also did my postdoc, by the way, they started focusing on assuming perfect localization, but external motion capture systems, in order to show that we can build controllers that can navigate drones at the limits of handling. Let me show you a very old video from 2010. This video got more views than Lady Gaga in 2010, in just less than 24 hours. It was showing drones playing tennis, super agile, but they were controlled by an external motion capture system. So these demonstrations are very useful to show that the platform is there, it exists. But what we are missing is software that analyzes images egocentrically, meaning from the perspective of the drone, not from the outside. So There have been works that have tried to use egocentric perception to fly drones more agilely than before. But as you can see, while they were relying on onboard sensors, they were not as agile as those relying on external perception. Where are human pilots? Here. Where do we want to be as a society? Here. Every roboticist dreams to build an autopilot that can be better than humans to sustain us. But now let's go back to the drone specifically. How do we control autonomous drones? So autonomous drones are controlled with a camera on board and a computer on board. Now, analyzing every single pixel would take too much time. So typically what we do is that we extract some features like corners, and then we triangulate these points to build a local map of the environment. And using this map, we can basically stabilize the drone. So the drone gets a position reference that then the position controller uses to stabilize the drone. What makes drones very interesting from a research point of view compared to ground robots like legged robots or autonomous cars is that drones are one of the few robot species that without seeing cannot even stand still. Think of a legged robot on a floor. It stands still without seeing a single image. But a drone that doesn't see an image will eventually drift and crash. So there are a lot of challenges to fly drones. Now, what are they? What are these challenges for vision-based drones, especially for vision-based agile drone navigation? Well, the first one is the so-called perception-to-action dependence. We don't think too much about it, but we do this as humans every single day. Consider a quadcopter drone. Let's assume that the camera is looking down, and this blue cone denotes the field of view of the camera. What is the yellow star? The yellow star denotes the texture that the drone needs to observe at all times so that it can reliably estimate its own position, velocity, and orientation. Okay? Now, a drone, like a quadcopter, is underactuated, which means you cannot orient yourself in any orientation, because if you tilt a little bit, it will move forward. For example, if you want to reach the goal, what the drone will need to do is that it will need to orientate its thrust vector, which is the vector perpendicular to the propeller axis, towards the goal. But by doing so, the drone will lose the visibility of the texture that it needs to stabilize itself. And what will happen? The drone will crash. How do you solve that problem? Well, you solve that problem by creating a synergy between perception and action, what we call perception-aware planning and control. And that's something that, for example, you don't work on if you rely on GPS or motion capture system. But the moment you actually work on egocentric perception, you have to face this issue. And drones raise this issue very clearly, because they don't stand with their feet on the ground. What does it mean from an agile robotics perspective? It means that when you fly very fast, you will need to select trajectories that will allow you to track features so that they are not affected by motion blur, so that you can estimate your motion. You can do VAO from those features. We're going to get back to this problem. So this is called perception-to-action dependence. Another problem that drones raise is the very large domain shift. You see, they do not observe the world from the same perspective as a car. You change the altitude. You change the roll and pitch angles. So you need to actually really increase your training data if you want to train, for example, your YOLO classifier. What else? When you fly fast, there are many unmodeled effects: motion blur, high dynamic range, and turbulent flow, which is very difficult to model unless you rely on computational fluid dynamics. But those of you who work on computational fluid dynamics, you know very well that using these tools can take hours to days of compute for a single trajectory. But we want to do this 30 times a second. And then there is another problem: latency. You see, when you use frame-based cameras, you are limited by the frame rate of the camera. The latency is set by the frame rate of the camera. What happens in between two frames? You don't know, because you are completely blind. Well, if you want to push the limits of agility, you would like, ideally, to know what's happening between two frames. Then there is another problem. We tend to think that robots like drones are rigid, but they are not rigid. They are soft when they fly agilely. Why? Because under the high accelerations that they experience, there is relative motion between the frame of the cameras and IMUs and the frame of the body of the drone. you are all experts in 3D vision, and you know very well that you know, an error in extrinsic camera parameter calibration of 1 centimeter can cause an error in state estimation that can be also 1 or 2 meters, depending on how far you are from the structure. And this can basically destroy your vehicle completely or endanger people. These are systematic errors. How do we take them into account? So let's now try to understand how drones are controlled. Drones are controlled like any other mobile robot. There are 3 software modules: perception, planning, and control. Perception does what we in robotics call state estimation. Vision people, they don't call it state estimation, they call it localization and mapping. Why do we call it state estimation? Because for us, it's not just position and orientation, it's also velocity. And for that, we also pair a camera with an IMU, an inertial measurement unit. But perception also does local 3D mapping. Then what is the planning module doing? The planning module uses this information from the perception module and outputs a trajectory to avoid the obstacles. However, finding this trajectory can be quite cumbersome. Why? Typically, for obstacle avoidance, you generate thousands of trajectories, and you compute for each candidate trajectory the collision probability. That takes a very long time, about 60 milliseconds. What if we wanted to do it in 1 millisecond or less? What can we do? What will be the significant breakthrough? And finally, there is control. Control is a module that is kind of solved, I would say, as making certain assumptions about your model, that if you give an input, a trajectory, then you want to compute the exact 4 speeds of the motors in order to follow the trajectory with centimeter accuracy. So that's how vacuum cleaning robots, autonomous cars, and drones work. But I argue that if you want to fly agile, this architecture is very fragile to imperfect perception. What would be the alternative way? The alternative way would be to do it like humans or birds, where you have a neural network that maps end-to-end sensory inputs like images and inertial measurement unit, I'm thinking of the vestibular system, to control commands. We know from nature that one day we researchers will succeed building an AI that will be able to map end-to-end sensory inputs to control commands. But even if we succeed, it will have a limited interpretability, and you will need trillions of images to train it for every environment, every task, and every robot. So what we've been trying to do at my lab over the past few years is trying to combine model-based approaches with deep networks. I'll tell you how in a little bit, but the problem when you start playing with deep networks, there are certain questions you need to address. Do you train these networks with or without supervision? Where do you get the training data? Can you get them in simulation? But if you train them in simulation, how do you address the simulation to reality gap? Rather than talking very abstractly, in my lab, we picked 3 tasks that are not the most useful, but they are important to measure our progress with respect to humans. We picked drone acrobatics, navigation in the wild, which in robotics it means navigation in unknown environments for which you don't have a map, and then autonomous drone racing. But we also needed a platform that would allow us to push the limits. So we reached out to drone racing experts. We started a collaboration with the Swiss drone racing champion, and thanks to him, we built Swift, which is the friendly name we gave to our AI drone. It's about 20 centimeters in diameter, so very much like first-person view drones. It's very agile. It can accelerate from 0 to 100 kilometers per hour in much less than a second, so it's much faster than a Formula One that needs 2.6 seconds to accelerate to 100 kilometers per hour. It can reach accelerations of 5 Gs. Consider that when you are flown from Cape Canaveral to the space station, you experience 3 to 4 Gs. Now we have a drone that can generate up to 12 Gs, by the way. And then for the eyes, we have an interior sense, and for the brain, we use NVIDIA Jetsons. Let me show you some videos, and then I'll tell you how it works. So thanks to the addition of deep networks to model-based approaches, we were able to achieve unprecedented agility. On the left, you can see a drone, our drone performing acrobatic maneuvers up to 3 Gs, even outperforming humans, for example, in trying to do the same maneuver but backwards. It turns out that for a machine it's super easy, but for a human it was very, very difficult to actually learn to do. And on the right, the same drone is flying in a forest at up to 40 kilometers per hour. Notice that this was the first time that these things were achieved outside of a lab and at these speeds in the physical world. So thanks to machine learning, we were able to fly twice as faster as model-based approaches and with much more robust performance against perception noise, for example, motion blur, missing data, than model-based approaches. How did we get to that? So we needed a lot of training data. It turns out you cannot train your deep networks in the real world because it takes a huge amount of data. And you would also endanger the life of your PhD students or the environment. So we turned into simulation. Simulation is fast, it's cheap, and most importantly, it's very safe. So in the amount of about one night, 8 hours, we were able to simulate the equivalent of 60 days of flight time without any interruption. On the left, you see the simulator used for acrobatic maneuvers, where we simulated 200 drones performing different acrobatics. And on the right, a different type of simulator, which evolved over the period of 3 years. Now we are using Unity or Unreal Engine, so we are benefiting from video game engines. And here we were training a policy that goes from perception input to control commands or trajectories to avoid obstacles at high speeds, so navigation in unknown environments. How did we train these agents? You see, one of the main problems with model-based approaches to do something like this is that, for example, for obstacle avoidance, you need to generate thousands of trajectories and compute collision checks. This takes a significant amount of time. In fact, the majority of the time is taken to compute collision checks, about 60 milliseconds. But we were able to shorten that to less than 1 millisecond. Well, how? By distilling the knowledge of a model-based expert into a neural network student network. This is how we trained it. We trained it with privileged imitation learning. What is that? So in imitation learning, you try to imitate an agent. But we didn't want to imitate a human because we wanted to outperform humans. So we imitated the best model-based approach, which is the one that generates these 40,000 collision checks. But it's very slow. But in simulation, you have access to the ground truth, right? So our imitation learning approach is privileged because at training time, the expert has access to the ground truth of the drone and of the environment. So he knows perfectly the state of the drone, position, orientation, velocity, as well as the position of every obstacle in the environment. And then we try to distill this knowledge into a CNN student neural network. What does the network regress? It regresses a trajectory. Now, why not regressing directly control commands? Well, we wanted to maintain some modularity, some interpretability, so that we know whether when there is a failure, the failure is coming from the planning module or the control module. So what we are doing is that we are only imitating trajectories, but then the control, so the following of these trajectories, the tracking of the trajectories, is delegated to a classic control approach, MPC, Model Predictive Control. The problem in training and simulation, though, is that there is a sim-to-real gap. Now, there would be a lot to talk about this. A key contribution of this paper was, these papers was that we reduced the sim-to-real gap by finding a suitable intermediate representation that would make the transfer zero shot without any fine-tuning in the real world. How did we do it? Well, for acrobatic maneuvers, we do not train on raw image pixels, but we train on optical flow vectors. For navigation in the wild, we don't train also on raw image pixels, but we train on depth maps. So these optical flow vectors or depth maps are specific for the task you want to solve. But they are very similar between simulation and the real world, so they reduce the sim-to-real gap. So what is the takeaway of this research? What we showed in this research is that we showed for the first time that you could distill a complex navigation strategy like flying at high speeds among obstacles in unknown environments into a neural network. We showed that the policy was much more robust than model-based approaches, and that this was made possible by an appropriate abstraction of the sensory inputs, either optical flow vectors or depth maps. The problem is that while the results are very good, we relied on imitation learning, which means we relied on the availability of labeled expert data, where the expert was an artificial expert. But now the question that we are trying to solve is, what if this artificial expert does not exist? So we had to find a task where the artificial expert does not exist. It's drone racing. Let me show you why drone racing is so difficult with Marvin, who started racing at the age of 12, and we started collaborating with him when we took this video when he was 15. He now won already 3 Swiss champions of drone racing and is considered one of the world's best pilots. So let me show you this nice video.
Get ready on the tone in less than 5. Beep!
So what you can see here is 2 things. First of all, they're always pushing the quadrotor to the limits of handling. Okay? Any little mistake can lead to a crash or a loss of the race. And it requires a very quick thinking and decision-making. So there is no time for other things. So these pilots have been training for this for many, many, many years. Okay? At the moment, there is no machine that can reach this level, unless you condition the environment. We'll get to that. So what is drone racing from a robotics point of view? In robotics, I would call it from an optimal control point of view. So drone racing consists in finding the control inputs, you can think of the joystick commands, to fly the drone through a sequence of gates in a given order in minimum time. So you want to reach the finish line as soon as possible. So in control, you want to minimize this big integral. Now, how will control people solve this problem? Well, if you assume that you have perfect localization, which we cannot assume because we are a 3D vision expert. If you had perfect localization, then the problem would be easier. Because then what you could do is the following. You could generate the time-optimal trajectory, which is truly time-optimal, which you can do because you know perfectly the layout of the gates. And drone racing pilots do because they have access to the race in advance, weeks in advance. So if you can generate such a time-optimal trajectory, it means that if you can stay on this time-optimal trajectory, you will be guaranteed to outperform any human on the planet, right? What's the problem? It's the assumption. If you had perfect localization, and you know very well perfect localization does not exist. Why? Well, the trajectory is optimal as long as you are on the trajectory. But as you know very well, if you use egocentric perception, you have drift. You have noise that causes drift. Additionally, there is turbulence caused by aerodynamic effects. And actually, you're not flying the time-optimal trajectory, but because of drift and aerodynamic effects, you're always taken out. So in principle, you will need to always replan a time-optimal trajectory. But taking into account the perceptual limitation is actually a big, big challenge. Why? Because we forgot also that there is this action to perception dependence. You cannot fly any trajectory. If you want to compute the time-optimal trajectory, in principle, you should know the deficiencies of your perception system, like motion blur. It means not every trajectory will be guaranteed to allow you to do state estimation, because you will have motion blur. But let's try to analyze the problem further. So what you see here is our state estimation pipeline. It consists of a VIO, which I assume everyone knows, visual inertial odometry, and a gate detector that is used for camera-based pose estimation. Let's look at VIO. In blue, you see the ground truth. In green, you see the VIO estimate. What do you observe? There is a big drift. You know how much the drift is? 20%. So it drifts 20 meters every 100 meters of trajectory. Ingenuity on Mars drifts about 1%. Why does our drift so much? Because we are flying much faster. We were flying up to 100 kilometers per hour, very close to the structure, so there is motion blur. And consider here there is also an IMU, which also drifts. So VIO alone is good locally, like within a few milliseconds, but not globally. That's why we combined VIO with a map-based localizer based on a gate detector. And we did this fusion with a Kalman filter. So we have a gate detector that detects the gate with a good neural network. And then the gate corners are fed into a PNP algorithm, perspective from endpoint, that can give you the pose of the drone with respect to those gates, which, remember, you know because the layout of the gates is known in advance. What is the problem of PMP? If you remember from computer vision courses, the uncertainty of PMP scales quadratically with the distance from the structure. And you see it very well here. This is the famous ellipsoid of uncertainty, only for position. You can see that as you get close to a gate, the uncertainty shrinks. When you get farther from the gate, it grows. And by the way, this uncertainty is not even taking into account the systematic errors I was telling you before, due to the fact that at high accelerations, the drone experiences this compression of the relative motion between the camera frame and the body frame. For these reasons, after spending 7 years in tuning model predictive controllers, guess who won the race? Not a standard model-based approach, but a neural network controller, a 2-layer MLP trained with model-free deep reinforcement learning in simulation, with a little bit of data in the real world. I'm going to tell you. Now I'm going to show you the simulation. It takes a few million iterations, during which the drone learns first to hover, then to fly, and finally to race. The simulation takes about, so the training simulation takes about an hour, and in this 1 hour simulation, we simulate 100 drones that are flying for the equivalent of 1 month of actual flight without any interruption. And we are training it with reinforcement learning, trying to maximize a very sparse objective that you see there. We are trying to maximize a reward that consists of 4 only terms. Progress, you try to maximize the progress towards the next gate. You want to now reduce motion blur and reward maneuvers that facilitate the perception of the next gates. That's the most important one, the second one. Then we have 3, continuity between the policies generated. 4th, you want to penalize crashes. So after 7 years of work, we felt confident enough to compete not just against Marvin, because we beat him in our arena. By the way, we built an arena for this, thanks to the ERC money. A huge arena, 30 by 30 by 8 meters. But then we invited to Zurich the best of the best drone racing pilots. We invited Alex Vanover, who is the one who shoots most of the Hollywood movies, drone sequences like Ambulance, Red Notice, Gran Turismo, and more. That's him behind the camera. We invited Thomas Bidmatta. Why 2? Because there are 2 main leagues, the Drone Racing League and the Multi-GP International League. So we took the best of each league. Then, what is important to say is that we built the AI drone and the human-piloted drone identical, according to the specifications of the world champion, so that it was a fair race. So the difference was only in the software, artificial versus human brain. The camera field of view was the same. The weight and the aerodynamics of the drones was also identical. If you have more questions about structural advantages, disadvantages, ask me at the end. There would be a lot to talk about. Then, another aspect which you need to take into account when you organize such competitions is the psychological aspect. You know, a lot of the energy that pilots put into these competitions comes from the euphoria, from the adrenaline that they get from having supporters like you all around. So we had to organize a public competition. We invited more than 1,000 people so that they could actually see that there was a crowd around them. Now let me show you the final one of the many races from the perspective of the human. The AI drone, Swift, is shown in blue, and the best of the humans, which was Alex Vanover, is the one in red. So they took off from the podium at the same time, more or less, but you could see already that the AI gained significant lead with respect to the pilot. Who won? Well, the AI won, otherwise I wouldn't be here today telling you the story. more importantly, what I have to say is two things. So the AI won, but it won with a significant lead with respect to humans, 0.5 seconds. The action lasted 15 seconds, by the way. So 0.5 seconds. Is this significant? Yes, it is, because in these competitions, the difference between first and second place winners is 0.1 second. Not only did Swift gain the fastest lap time, but it also won the largest amount of races, 15 out of 25. The papers were published in Nature and Science Robotics. And in the Nature paper, you will find also the statistics. By the way, we recently released all of them. And we encourage people working in 3D vision like you to actually use these trajectories, because we released all the data, IMU, images, ground truth data of drones flying up to 100 kilometers per hour, both indoors and outdoors with motion capture systems as a ground truth. And we have also removed the ground truth so you can actually test against our algorithm, and also try to show your score in the leaderboard. Then, however, was it sufficient to train in simulation? No, it was not sufficient. As you can see, there was a sim-to-real gap. So sometimes it's difficult to visualize in robotics the sim-to-real gap, but here it was very easy. In orange, you see the trajectory expected to be flown from simulation, and in purple, the actual trajectory. Where is the gap coming from? Well, there are two sources of errors, I told you, if you remember. Perception residuals, there are systematic errors, and then there is also turbulent flow. And there is no simulator that can capture that turbulent flow. The air is chaotic. The only way to do it would be to use a CFD, computational fluid dynamics, but it would take hours for each trajectory, so you cannot do that. We have to do it at 30 times a second. So what we did, and that's the one takeaway of the Nature paper, is that we do fine-tuning from previous rollouts. What do we do? When we train the policy the first time in simulation and we deploy it in the real world, we are not able to outperform human pilots. We are missing that epsilon, that gap. Why? Because simulation doesn't capture those residual, perceptual, and aerodynamic residuals. So what we do is that we cheat a little bit in the first deployment in the real world. We use a motion capture system to record the ground truth data, and then we use Gaussian processes to model the residual perception and aerodynamic effects. Then we go back to the simulator. We now augment the simulator with this Gaussian process, learned from previous real-world rollouts. We fine-tune the policy in this augmented simulator, and finally, we deploy the policy vision-based entirely on the real drone. And now it outperformed the humans. What else? What was the second takeaway? So we worked for 7 years on optimal control, but eventually the solution came from reinforcement learning, from using a neural network controller. In another paper published in Science Robotics, we delved into the reasons why RL outperformed optimal control. The key findings in 2 sentences is that basically the problem of optimal control is that it relies on the decomposition of the problem into planning and control. Basically, every controller relies on a reference trajectory. So this reference trajectory biases the final results. It does not allow to discover maneuvers that humans haven't thought of. In fact, at some point, one of the human champions challenged the AI to actually fly a different layout of the gates that he invented. And to his surprise, the AI again found the trajectory was impossible for any other optimal controller to find, and even for the human. But we can talk about it if you want. Additionally, RL exploits domain randomization as simulation time. So you randomize all the features you want your controller to be invariant to, like the systematic errors. And these allow the RL to, again, shine with respect to optimal control. Does it mean that the game is over? Well, there are many things to talk about if you're interested. First of all, we are not saying we have solved drone racing autonomously, because the competition was conceived in a closed hangar. We control the illumination, control turbulence. I would say that there are a lot of scientific aspects to explore. Swift was computing its state, position, velocity, and orientation explicitly. Humans don't do that. They go directly from visual inputs on the screen to control commands. We would like to be able to do that. What does it take to be able to do that without explicit estimation? We don't know. And there are, anyway, other problems, robustness and versatility. Robustness means it doesn't work 100%, and it still works in this enclosed environment. We cannot still generalize to any unseen environment. versatility is another problem. If you change the layout, you need to retrain. And how do you now generalize to other problems of drones, which is beyond drone racing, like, I don't know, package delivery, crop spraying, and other things? So we are not working on everything, but we are addressing a little bit robustness. But just to make you remember how difficult it is to do research on robotics, and especially drones, consider that we wouldn't have achieved these results without failing thousands of times. These are just some of the spectacular crashes that we have recorded. We have hours of crashing. But we are not the only ones. You know, if you want to succeed, you really need to push hard. If you haven't crashed and destroyed your robot, it means you haven't pushed hard enough. So where are we compared to human pilots? Well, we are still far from human pilots in everything, in many things, versatility and robustness. So there are still decades to go. But where else are we working on? And if we could address something, because we cannot address everything in robotics and computer vision, what could we do? Where could we actually take inspiration from? Is it only human pilots, or is there something better than human pilots? Well, birds are certainly better than human pilots. Why are birds better than human pilots? Because they sit on the aircraft. They do not perceive the world to the frames of the camera, like human pilots. Human pilots have a camera that relays the images, remember, to the screen every 30 milliseconds. Birds don't do that. They sit on the aircraft. They receive the visual information continuously in time. From a perception point of view, what limits the agility of a robot is the latency of its sensors and algorithms. For the sensors and algorithms, there are two types of latencies: processing latency and sensing latency. The processing latency is the time that you need to wait until the image has been processed. And the sensing latency is the time that you need to wait until the next frame arrives. And that's given by the frame rate of your camera. Now, most machine vision cameras used in autonomous driving and robotics have a frame rate of 30 or 60 hertz. However, our phones can go up to 1,000 hertz. So a typical argument would be, OK, just go for a 1,000 FPS camera, and then you have a latency of 1 millisecond. Everyone agrees? What's the expense of that? Bandwidth. That's our problem, the bandwidth. You see, when you pick a standard camera, you can tune the frame rate. But if you want to reduce the latency, you have to sacrifice your bandwidth, because bandwidth is inversely proportional to the sensing latency. If you want a low bandwidth, you sacrifice the latency at the cost of reducing the safety of your autonomous car or your drone. So that's the problem with the camera. Once you select the camera, you can only move along this hyperbola. Event cameras are a camera that allow you to get off this curve. You can decide the bandwidth, you can decide the latency. What is an event camera? An event camera is a camera that measures only motion in the scene, and it does so by using smart pixels that only trigger information whenever a pixel detects motion. How do they do that? Well, every pixel checks whether there is a change of intensity that can be positive or negative, and then that pixel will trigger information when the change of intensity has been recorded. So if I'm moving my hand in front of the event camera, the output would be these dots of positive or negative changes of intensity, but they are coming with microsecond resolution. Yes, because the output is not frame-based, it's continuous in time. Let me show you what I mean. Imagine that the visual stimulus is a rotating disk. The output will not be frames. It would be a stream of asynchronous events in space and time, what we call a space-time volume of events. But the beauty of this thing is that if nothing moves, there is no information triggered. So you have a drastic reduction in bandwidth. And another cool thing is that there is very negligible motion blur, which is very important for agile robotics. But the most important thing you must remember is you get a continual flow of information, continuously, with microsecond resolution. What's the downside? Well, you cannot apply directly computer vision algorithms. You need to develop new ones because the sensor nature is asynchronous. So how do we process events information? Well, at the moment, there are two main paradigms, and we published them in a survey paper on event-based camera a few years ago with all the best people in event-based vision. There are two paradigms. Those methods that process events one by one, and they exploit the measurement model of the event camera that says an event C is generated whenever the difference of intensity at the same pixel between two times is equal to a given threshold. By doing so, you can do amazing things. You can do event low latency feature tracking in the blind time between two frames. And that's what we published, for example, at CVPR last year. Another school of approaches is so-called batch methods, that in contrast, they process all the events in a volume in space and time. So this is not X, Y, Z. This is X, Y, and time. Do you know what visual stimuli generated this event? A person. So batch methods try to distort the space-time volume of events according to the direction of motion that generated those same events. You can do this by solving an optimization problem, where the unknowns of the problems are the parameters of your algorithm, structure from motion, SLAM, whatever you want, homography, optical flow. So there are many, many flavors of this and many, many papers. We call this type of methods that exploit contrast maximization, because they work by trying to maximize the focus, the contrast, of the resulting image. By the way, these methods now are the main ingredient for training self-supervised approaches for event-based neural networks. Now, let me show you some, before finishing, let me show you some interesting scenarios that event cameras are unlocking thanks to their low latency and negligible motion blur capabilities. Let's go back for a moment to drones. One key aspect that people fear a lot about drones is that potentially they could crash from the skies when the number will be significant. This is something happening. It's just that there's not so many drones flying over our heads. But a few years ago, GoPro bought a company doing drones, and they were not mature enough, and the drones started crashing from the air. Sometimes these drone crashes are actually caused by a motor failure. If one motor of a quadcopter fails, the drone starts spinning on itself like a ballerina, because of the principle of conservation on the angular momentum. People have shown, though, in the past, that if you have a perfect position reference from GPS, then you can stabilize the drone unstably, which means the drone will still be spinning, you cannot counteract that, but will still be spinning on the spot without drifting and crashing. Until then, it was not possible to do it with a standard camera because of the motion blur involved. We showed that thanks to the event camera, you can finally do this. Now we induce the motor failure, so the drone started spinning like a ballerina. Now you will see that the standard camera generates so much motion blur that the features are condensated in the center of the image, where the motion blur is ideally 0. But thanks to the no motion blur capability of an event camera, you can actually reliably detect and track features. And you can do so, even at this significant speed, to a point that we were not only able to stabilize the drone without GPS, without motion capture, we were even able to control the drone to fly a straight line trajectory back and forth. We released the code open source because we hoped that this could help many companies, making drones safer. What about another interesting safety feature for autonomous cars and other robots in general? For example, dodging obstacles. So drones are particularly agile, so an event camera is quite interesting. It opens interesting problems. Can you avoid a ball being thrown at the drone? Well, we showed that thanks to the low latency of the event camera, we could do so with a latency of 3.5 milliseconds. We didn't use any frames. If we were using a frame-based camera, we would have needed at least 2 frames to localize the ball in space, right? You need 2 frames and to estimate its velocity. How did we do it? This is the space-time volume of events, and this big shadow that you're going to see here in a moment, this is the ball. You can zoom in the time dimension, and then the interesting thing is that the event rate is related to the relative speed of the ball with respect to the drone. So you can infer that either with statistical methods or machine learning methods, up to you. We showed last year that we could invert the policy, and instead of dodging the ball, you can catch the ball. And we did this with Professor Marco Hutter from ETH Zurich. But let's move away from drones. It's not just drones that are benefiting from this. This is a recent research from Professor Zwairi at the Khalifa University in Abu Dhabi in collaboration with Boeing. They have a lot of wings for Boeing planes that are being manufactured there, and they need to drill holes. And after drilling holes, they need to check every individual hole. They typically use a LiDAR and cameras. But for doing so, you need to stop in front of every screw and move to the next screw. So there is this stop-and-go motion. Let me show you what I mean. This is how the drone operates. There is a high-resolution camera that takes pictures and stops at every hole. But with the event camera, you don't need to stop. That's the idea I wanted to convey here. You can basically increase the productivity of this robot potentially by a factor of 10. That's what I show in this paper, by the way. Going further, what is now missing? I think most of the research on event vision was done on event cameras alone. Now, in the last 2-3 years, people started looking at combining event cameras with standard cameras because they are complementary. Why? Because event cameras are high-pass filter sensors. They convey the varying component of the visual signal, while cameras convey only the static component. And this is a paper that is about to appear. It's about low latency automotive vision between 2 frames. The idea is to continuously detect a person or a vehicle in the blind time between 2 frames, either using the information from the last frame, or even if the person appears in the blind time between 2 frames. And we do this using asynchronous graph convolutional neural networks in an appropriate way. So what's now the future of event vision? Event vision started in 2008. It was invented at the University of Zurich, but the resolution was very small, 100 by 100 pixels. A French company called Prophecy, they improved the resolution 10 years later. Apple, Meta, started publishing a lot of patents. Only Apple alone has more than 100 patents on event vision. In 2021, Sony, Samsung, OmniVision, which are some of the biggest camera manufacturers, they started also investing in event cameras and also commercializing event cameras. Meta opened an event-based sensing lab in 2022. ESA, the European Space Agency, put 3 event cameras on space. And last year, Prophecy announced a multi-million-dollar deal with Qualcomm to put event cameras on phones. On the academic side, event cameras are getting popular, but there are still a lot of unsolved problems, like how do you ensure now a hardware that can really take advantage of this asynchronous and low latency, latency of the camera. Anyway, I would like to thank you for your attention, and I would like to thank my team, without which I wouldn't be here today. Thank you very much.
Is it working? Yes? Is it working? Yeah. Thank you very much for the awesome talk, really. Like, it's such a great to see a 3D application, or application of 3D computer vision in robotics. So we have about 5 minutes for questions before moving on to the oral. So if anybody wants, raise your hand and I'll come to you. No? Yeah, over there, yeah. Raise your hand higher so I can see it.
Hi, thanks a lot for the talk. Have you considered usage of tricopters or, I don't know, copters with different number of propellers? And another question, do you think, can some analogous approaches be used for like motion, I don't know, for prediction? Like the biggest problem in in motion prediction, in trajectory prediction, was that it is very slow. But if we used some techniques that work not digitally, like with vectors, with matrices, but somehow analogous, understanding the flow of the wind and stuff like that? Thank you.
So the first question about, have you considered the other multicopters, like tricopters or other? Yes. So we have a collaboration with, the Volocopter from Germany, which has 18 rotors. So the same concepts also generalized to that. I would say that the more rotors you use, and sometimes the problem easier it gets. Why? Because if you have more than 4 rotors, then sometimes, depending on the configuration, if at least one rotor is out of the plane, then it's no longer under-actuated. So you can actually hover in any orientation. So the problem actually facilitates rather than getting more difficult. Another problem we're actually considering is putting a gimbal on a drone. At the moment, the camera was rigidly attached, and that actually complexifies things a lot. Your second question, what about motion prediction? So in robotics, prediction of the future is very much used in robotics. And in robotics, you remember that you have a prior. You know your model. You know, more or less, you have a model of the aerodynamics, which, of course, is not perfect, but you have a certain model, so you can actually make physics-informed and prior-informed predictions into the future. This is something that some robotics start exploiting.
All right, any other questions? No, I do have a question myself. So Dinesh Pai at UBC had this like super cool research about fixation points and automatic updates of fixation points for high-speed capture. So most of the research you've been doing on high-speed capture is purely based on event cameras, but isn't there a hope to actually merge the two ways of approaching the problem, where you decide where the camera is looking, keep the fixation point, and then combine that with?
Absolutely, absolutely. No, this is also, so it's an active vision problem that you're mentioning, where basically now you put a motor underneath the camera and you can basically fixate. So yes, this is, again, a problem of tight coupling of perception and action, and then you want to basically focus the attention over there. Consider, though, that if you fixate perfectly, then there will be no event generated, right?
But that would be the point, right?
But
So
that's a reason also to combine with
each
standard cameras. So by the moment there would be an oscillation or a shaking, then the events will be generated. So another reason to combine event cameras with standard cameras.
Thank you. I think we can move on. Any other question otherwise? One last one, maybe?
Yeah, over there.
Hi. So my question about regarding the computational fluid dynamics calculations. So the traditional way, it takes so much time. However, there are also neural network approximations real time. Have you ever considered that?
Yes. Thank you for the question. I was waiting for this question. So that's a problem, indeed. So how did we achieve, how did we capture the aerodynamic effects, residuals that our simulation does not capture? So over the past 5 years, we worked on accurate simulators of the vortices around the vehicle. Without going too much detail, we use blade element momentum theory, where the idea is that you take the propeller, you model it as a finite number of small elements that rotate about one axis, and then through standard aerodynamics, you try to model the folding, the bending of these propellers. But unfortunately, blade element momentum theory can only explain so much about the residual forces and torques acting on the propellers, about 60% only. So what we did is that we flew the drone in our motion capture arena. We recorded a lot of data, from slow motion to high-speed motion, and we trained a neural network that was trying to fill the gap between the desired trajectory and the actually flown trajectory with a TCN, with a simple TCN. Well, with the neural network, we were able to actually explain a residual 30%, but there's still another residual 10% that we are still working on. That doesn't mean, however, that we have solved it, because these aerodynamic effects are very much trajectory dependent. So it's very easy to get outside of the training distribution, okay? But nevertheless, it's a small step in that direction.
All right, it is time to move to the oral session. So let's thank again once more